In our previous lecture, we have studied the effect of AC voltage source on an RL circuit. We also saw what is the type of response which we get whenever an AC voltage source is applied to an RL circuit. That is the natural response as well as the forced response or the steady state response. We also saw that similar kind of response would be seen for a synchronous machine also, but it was pointed out that there will be some differences between a simple RL circuit and a synchronous machine. Now let us see what were those differences. As we have seen in our one of the previous lectures, that the equivalent model of a synchronous generator is usually given by an AC voltage source in series with its synchronous reactance. So whenever there is a short circuit fault on the terminals of the synchronous generator, I am showing the per phase network equivalent model. So whenever there is a short circuit on the terminals of the generator, the network is kind of purely reactive. So if I take some small resistance also, so we will see that this circuit should behave like an RL circuit only, which we have seen in our previous lecture. But what are those differences? Now let us discuss those. One of the best ways to see the effect of short circuit on a synchronous generator is to study the oscillogram of the currents on the various phases of the synchronous generator. Now here in the figure I have shown the sample of an oscillogram which we will obtain if the DC decaying part, that is the natural response, is eliminated or it is not included. That is, either we are taking a phase in which alpha minus theta is equal to 0 or n pi. Okay, so because of that the DC component will be 0, and here we can see that the currents are symmetrical about the t-axis. The frequency of the currents are also equal due to the little bit difference in the intervals during the drawing. The frequency might not appear equal, however the frequency of currents is equal. These partitions are equal everywhere from here to the end point. So we should note that in the sample shown here, the DC current has not been taken into account. Either this is the case or we have just eliminated it so that we can understand the type of current appropriately for a short circuit on a generator. Now let us say this is phase A. Then phase B and C will be having DC currents. Why? Because phase B and phase C will be having voltages which are 120 degree apart. So alpha minus theta cannot be 0 for those phases. So because of that, those phases will be having a DC decaying component. Because of that, what will happen? There will be a DC decaying component like this, whose time constant will depend upon the time constant of the armature winding, and this kind of current will be superimposed on this. That is what we will get. We might get some current like this. Something like this. That is, the currents might not be symmetrical about the t-axis. They will try to be symmetrical about this DC decaying current. These can even cross this line depending upon various magnitudes. So the currents in other phases will not be symmetrical about the time axis. So this point should be noted. Now here I have shown a typical oscillogram of a phase in which short circuit has been taken. Now I have tried to show this oscillogram in 3 colors. First color is comprising of just first 2-3 cycles, rather 1 and 2 cycles. Okay, so we see that the green color is trying to represent first very few cycles, maximum 2-3 cycles, and the color blue is trying to show the later cycles, and black color is trying to show the steady state. Now corresponding to these amplitudes, let us say this is the origin O, this steady state amplitude let us say is OA, and if I extrapolate this blue part, this blue decaying part, and let us say this point is B and the maximum point is C. Okay, then corresponding to these points we define OC as maximum momentary symmetrical short circuit current. So why symmetrical? As I already told that we are taking that phase in which there is no DC decaying component. So this is the OC is the maximum possible momentary value of this short circuit current. Okay, now this is the steady state value. If I extrapolate this and neglect the first few cycles, I will see that current would have followed this path and it would have reached OB. So this OB represents the maximum value of the transient current. If there would not have been any sub-transient component, then this would have been the maximum value. Okay. However, in a synchronous machine, when it is short circuited, the initial value of current in first few cycles is very high, and that part is called sub-transient part. So up to this I am trying to show the sub-transient part, and up to this I am trying to show the transient part, and here I am trying to show the steady state part. Now in a synchronous machine, due to the flow of current in the armature, there will be change in the air gap flux due to the armature reaction. Because of that, the voltage induced will be different. So to cater those differences, what we do, we define various reactances offered by the machine. Okay, and we define 3 reactances. First one is the sub-transient reactance. Second one is the transient reactance. And the final one is the synchronous reactance, the steady state reactance. Now for a round rotor machine, this can be replaced by simply XS prime and XS double prime. Now we will study it in detail when we will study the synchronous machine part in our electrical machine course, that whenever we are dealing with that current which is approximately 90 degree out of phase with the induced voltage, then we take the direct axis reactance. So since the circuit of the synchronous generator on a short circuit is quite inductive, rather it is very close to being purely inductive, that's why we take the direct axis reactance for a salient pole machine also. So this is the reason why we show these reactances by XD, XD. This D refers to the direct axis reactance. Okay, we will also study this in detail in our next lecture. Now, from this oscillograph, what we will do, we will try to define these three values. XD double prime is usually shown by the ratio of the voltage over the sub-transient current. Okay, similarly this XD prime, the transient reactance, is usually referred or defined by this ratio, the induced voltage over the transient component of the current. Here I am trying to show the magnitudes of phasor only. For the definition part, we are just dealing with the magnitudes only. Similarly, this XD is nothing but the induced voltage at no load. This is the induced voltage at no load. We are here dealing with the case when there is no load on the generator before the fault occurs. Okay, and this is the steady state component. Okay, now as we have already seen that we will follow the convention that during the phasor representation we will represent the RMS values only. So here these values OA, OB, OC, these all represent the maximum values, the maximum amplitude possible for various cases, like OA represents the amplitude in steady state, OB represents the amplitude in transient stage, and OC represents the amplitude in the sub-transient stage. So to convert these into the RMS, what I will do, I will divide them by √2. So it implies that XD double prime can be written as the magnitude in RMS of the no load induced voltage over, what is this value? This will be OC over √2, or XD double dash can be written as √2 times the RMS value of the induced voltage at no load over OC. Similarly, XD prime can be written as √2 the RMS value of the no load induced voltage in the air gap over OB, and the normal steady state reactance can be written as simply √2 EG over OA. So these three equations, this equation, let us say equation number 1, this is equation number 2, and this is equation number 3, are the defining equations for the various type of reactances offered by a synchronous machine during a short circuit. Okay, and these can be calculated through this oscillogram. Now we will try to see why different kind of reactances are being offered by a synchronous generator during a short circuit. That we will see in the next slide. As we know that during steady state, the synchronous reactance of a machine is actually composed of, if I am writing for a round rotor machine, it is nothing but the leakage reactance and the armature reaction reactance. Okay. So during steady state, and for a salient pole machine, if I want to write just for the direct axis reactance, because we are going to deal with direct axis reactance only, since the short circuit current is quite about 90 degree out of phase with the induced voltage. So we are going to deal with the direct axis reactance only. Now, what happens when there is a short circuit? Then the previously no loaded generator will start carrying current in the armature winding. So there will be an armature reaction, which will try to reduce the air gap flux and the induced voltage. But as we know that due to Lenz's law, this change cannot happen instantly. So because there will be an opposition to this change. Because of this, what will happen? Let us say this is the armature of a synchronous machine, and I am trying to show a winding. Okay, and let us say this is the rotor of that machine. So what will happen? There is a field winding on this rotor, which is carrying DC current. Okay. Now this rotor is provided with the damper bars or the damper winding. Okay. Now when suddenly there starts a current flowing through this coil, what will happen? It will try to induce a flux which is going to oppose the existing flux. So to avoid that thing, due to Lenz's law, what will happen? There will be induced eddy currents in the iron, as well as there will be induced currents in the damper bars and the field winding also. So there is some kind of transformer action, and because of this, during the short circuit, the sub-transient reactance will be comprising of two more parts: the reactance of the field winding and the reactance of the damper winding. And due to the transformer action, we will try to show this in parallel to the direct axis reactance. Now, we know that the time constant of the damper winding is actually quite small as compared to the field winding time constant, which is highly inductive in nature. So, what will happen? This part will die out within first few cycles, and what will remain? Only the transient reactance of the machine, which can be shown by this only. Now here what I have done, I have assumed only unity turns ratio between various windings, which is actually not the case in an actual machine. But to show the concept why the various kinds of reactances are presented by the machine during a short circuit, I have tried to show only unity turns ratio between various windings. Now this damper winding and eddy currents die out very fast. Then the decay is governed by the field winding time constant, and finally in steady state only this is presented, the direct axis reactance is presented to the short circuit current. Now because of this, xd double prime is smaller than xd prime, and these are very smaller as compared to the steady state value. Okay, typically this value can be 0.15, this value can be 0.25, and this value will be around 1.1 per unit. So you see that these values are very different with the steady state values. Now there is one more thing to see, that since xd double prime can be shown or thought of as a parallel combination of three different reactances, so its value will be smaller than the maximum value available. That's why the parallel combination here is going to have a lesser value than this, and this is going to have lesser value than this. So you see, in this way we can see that xd double prime will be smaller than xd prime, and xd prime will be very much smaller as compared to the steady state value. Okay, now in the next slide what we will do, we will try to find some kind of mathematical expression for this kind of current. Now let us see how to find some mathematical expression for this kind of current. We will see in our next lecture that this decay, this OB decay can be shown to be exponential in nature. Similarly, this OC decay can be shown to be exponential in nature. Now what I will do, I will try to write this current. IT can be written as sum of three currents: OA sine omega t plus alpha minus theta. This term will be common for all of these currents, so I have taken it outside the bracket, plus this part AB. This AB is going to decay exponentially with a time constant depending upon the field winding. Let us say it is tau d prime. Similarly, this BC will decay exponentially with a time constant depending upon the damper winding and eddy currents. This is going to be BC E minus T over tau d double prime. Now from this figure I can say that AB plus OA is equal to OB, or I can write that AB is nothing but OB minus OA. Similarly, I can write BC is nothing but OC minus OB. Okay, now we know that OB, this OB is the maximum value of the transient part. So what it can be written as? It can be written as root 2 times the RMS value of the induced voltage over the transient reactance, and this OA is nothing but the RMS value of the induced voltage over the steady state reactance. Similarly, this BC is nothing but root 2 times EG over XD double prime minus EG over XD prime. Now I have got values for AB, BC, and OA I already know is nothing but root 2 EG over XD. So I will put these values 1, 2, 3 in this equation, and I will get the numerical expression for the IT, which I will write here. So IT is nothing but root 2 I will take common outside because it is present everywhere. And EG is also present everywhere. So I will take EG also common. This is the RMS representation. And this is the maximum value. So what I will have 1 over xd double prime minus 1 over xd prime plus 1 over xd prime minus 1 over xd plus 1 over xd. Now this is going to decay with the sub-transient time constant depending upon the damper winding and the eddy currents, and this is going to decay with the time constant depending upon the field winding. Okay, and here is the sine omega t plus alpha minus theta. So this is the mathematical expression for this kind of current. Now I have told that there will be induced currents in the field winding and the damper winding. So what kind of waveform we can expect in the field winding? As we all know that the field winding carries a DC current. Okay, so before this short circuit happens, let us say this is the DC current, a steady value, constant value in the field winding at some value IF naught. Okay, now when there is an induced current, this induced current cannot change instantly. So what it will do, it will try to rise from this point and it will have harmonics of double the frequency. That we will see in detail when we will study electrical machines subject. Okay, and this will decay with the time constant of that of the field winding. So this kind of current we will see if we will draw the oscillogram of the field winding current. Okay, now we are going to show in the next slide the relation between the leakage reactance and the sub-transient reactance. Now let us see the relation between the sub-transient reactance and the leakage reactance of a synchronous machine. Now initially, when the machine is at no load, the air gap EMF is equal to the no load generated voltage EG. Now when there is some current flowing through the generator armature winding, what will happen? There will be an armature reaction which is going to create some voltage, let us say EAR. Okay, now this EAR will depend on the power factor of the current which is flowing in the armature winding. So during a short circuit, this thing, since current is 9 degree out of phase, this thing is going to oppose. That we will see in detail when we will study the synchronous machine, that this armature reaction induced EMF is going to oppose the no load generated voltage. So the final steady state value of the air gap EMF will be EA is equal to EG minus EAR. Okay, now the steady state current will be simply EA over the leakage resistance, the armature winding resistance and the leakage reactance. So this is the steady state current which is going to flow in the synchronous generator armature winding. I have taken the final air gap EMF here instead of the no load induced voltage in the air gap. That's why there is no synchronous reactance here. Okay, so you see that during steady state, this I is nothing but, if I neglect RL, this I is nothing but proportional to the steady state air gap EMF and the leakage reactance. Okay, so let us say this is equation number 1. Now, when the machine is previously at no load, the air gap EMF is going to be Eg. Okay, but let us say now there is a sudden short circuit on the machine. What will happen now? To keep the flux constant, the air gap flux constant, there will be induced flux in the field winding, the damper winding. Okay, and there will be induced flux due to the armature winding also. So what will happen? The air gap flux phi will try to remain constant, but there might be some saturation also, and there will be increased leakage flux. So because of that, the flux linking the field winding and the armature winding will reduce from the actual initial value. Let us say initially this machine, this armature winding and field winding are having a flux phi in the air gap, which is linking with each other, these two windings, and because of this some Eg is being induced in the armature winding. Now there is a sudden short circuit, so current will flow through this armature winding. Okay, and this will create a another flux which is going to oppose this already existing air gap flux. Now there cannot be sudden change, so what will happen? There will be another induced current in the field winding, which will try to induce more flux. Similarly, there will be induced currents in the damper winding, which will try to induce more flux. So there might be saturation also in the core. Further, leakage will also increase. So what will happen? The total value of flux from the field winding, the damper winding, and the air gap flux will be constant and will be equal to the initial value of the air gap flux, and this is phi leakage also. However, the flux linking between the field winding and the armature winding will reduce, since these three are not going to participate in the induction of the voltage in the armature. So because of that, what will happen? The final air gap voltage, the final air gap induced voltage EA during the short circuit will be actually smaller than the no load induced voltage. Let me call this as the sub-transient induced voltage in a previously unloaded synchronous generator. Now the short circuit current will be simply XD double dash, and I know, sorry, not XD double dash, XL, since I am taking the final induced voltage in the air gap. Now I also know this current can be written as Eg over XD double dash. Okay, so you see that the initial sub-transient current can be written as either this EA double dash, which is smaller than Eg over XL, or it can be simply written as Eg over xd double dash, which we have seen in this lecture only. So comparing these two, I can see, I will take the ratio here, Ea double dash over xl is equal to Eg over xd double dash, or xd double dash over xl. Xd double dash over xl is Eg over Ea double dash. Now you see that I have already told or shown this, that this Ea double dash is smaller than Eg. It implies xd double dash is slightly greater than the leakage reactance of the machine. So this is the relation between the leakage reactance of the machine and the sub-transient reactance of the machine. That is, it is slightly greater than the leakage reactance, because this thing will have a very small effect. The effect will not be that much. So that's why this thing is slightly smaller only.